Hi everybody, welcome to another video in differential equation, section 3.2. On this chapter 3, we study application problems of differential equation. Right, so in this section we study two important things. The first one is the mixing problems, and the second one is population. So mixing problem. So the idea is we have a tank of, let's say, water. See, there's the tank of water, or maybe there are some salt in it, for example, and then we have something that flow in, another solution that flow in. The concentration might be different than the concentration of what it is currently in the tank, and then there's a valve that go out. So we're interested in the problem where we find the concentration or the amount of a substance or the solute in the tank at time t. So this is a problem that constantly changing. We have some solution originally and we have some different solution flown in, and the tank is stirred constantly, so the concentration will be the same throughout, and that concentration will flow out, and we're interested to know the amount at time t. So that's what we have. So let x of t be the amount of the solute or the substance at time t. We have the input rate and then the output rate. The rate, of course, is the derivative at which the amount of solute changes. Is the net rate of course, the input rate minus the output rate. In general, the rate is equal to mass over time. The mass, of course, x of t is the amount of the substance, usually a mass, and the rate is the mass over time, because x prime of t is dx over dt. Dx is the change in mass and dt the change in time, so that's why the rate is mass over time. And the mass over time depends on the flow rate times the concentration. Concentration is equal to mass times volume, and the flow rate is the volume over time. So let me write those two important formulas. So concentration is the mass over volume. And then the flow rate is the volume over time. So I have those two formulas. These two formulas together give us the rate, because if we cancel out the volume, we have mass over time. So that's what exactly the rate is. So we have these two. Let's just look at simple example. Let's say we have the flow rate of 2 liters per minute. And then the concentration is at the time is 2 kilograms per liter. Then when we multiply these two together, we have the rate. When we multiply this together, we have 2 times 2 is 4, kilogram per minute. So in 1 minute, the flow with the concentration will give us 4 kilogram that entering the tank or exiting the tank as 4 kilogram per minute. So we just multiply these two together. So that is the relation between the flow rate, concentration, give us the rate in general. So let's look at the problem. So consider a large tank holding 1,000 liters of pure water into which a brine solution of salt begin to flow in at a constant rate of 6 liters per minute. So that's just like a salt solution. The solution inside the tank is well stirred, is flown out at 6 liters per minute. If the concentration of salt entering the tank is 0.1 kilogram per liter, when will the concentration in the tank reach 0.05 kilogram per liter? Right. So this mixing problem, the first thing always is we let something to be the amount or the mass of salt at time t. So x is the dependent variable on t. The concentration of solution in the tank at time t is the concentration is mass over volume is the mass over the volume, 1,000 liters. One thing to note that in this problem, the flow rate that coming in, so the in rate of 6 liters per minute and the out is the rate of 6 liters per minute, meaning that it goes 6 liters per minute in and 6 liters per minute out. So the same amount that going in, the same amount going out. So that's why the volume is constant, because the volume is 1,000 unchanged, 6 liters in, 6 liters out for every minute. So that's constant. So let's write this little note: 1,000 liters, because flow rate in and out are equal. Yeah. So that's why it is constant, 1,000 liters. Now, so as we summarize the problem, the flow rate 6 liters per minute at that concentration, 0.1 kilogram per liter, we're entering the tank, and 6 liters per minute exiting the tank, and the concentration is whatever the amount of salt over 1,000 liters. Now, the problem is, as one thing that underrated in the problem is that we have to assume that, where was that? Okay. The solution is well stirred, meaning that the concentration will be equal throughout the tank, and that's very important. Usually if it flows from the top, the concentration will be different from the top to the bottom. Of course, if that is the case, it will be extremely difficult to do the problem. So we assume that it is well stirred, so meaning the concentration on the top when it getting in and the concentration at the bottom when it getting out will be the same. Otherwise, it will be very difficult to solve this problem. Right, so again, that's how we summarize the problem. So the rate in, flow rate time concentration, 6 liters per minute, 0.1 kilogram per liter, multiply, give us 0.6 kilogram per minute. The rate that exiting the tank, flow rate time concentration, flow rate concentration, give us that. And finally, the net rate is the rate in minus the rate out. So subtract that and we have a differential equation. Of course, if we drop the t, the equation becomes, or we just write x derivative is equal to 0.6 minus 0.006 x. So that is the equation. It's not that bad. Next, what else do we know? Right. the problem says when the concentration of salt in the tank will reach 0.05 kilogram per liter. So we need 0.05 kilogram per liter concentration in the tank, meaning that the mass is the concentration times volume. So we have concentration earlier. Concentration is equal to mass divided by volume. So the mass is equal to concentration times volume, and so we need 50 kilogram of salt in the tank. Right. So the problem becomes the initial problem. This is the differential equation. X of 0 equal to 0. Why do we have this? Let's look at the problem. Well, where did we get that? It said, consider a large tank of pure water. So originally there's no salt in the tank. So that's why this is X of 0 equal to 0. So initially there's no salt in the tank. So that's why we have this. And finally, we solve for t so that x of t is equal to 50. Right. Now on to solving that initial value problem. We have this, and this is separable equation. So move the x over one side and the dt and t on the other side. Integrate both sides. And I use substitution on the left-hand side and end up with this. And this is still a constant, so I just say that is a constant. And raise both sides to the power of e. And then we have that. And once again, this one is still a constant. And so that is a constant times this. And since u is equal to that, finally we do the back substitution. And we have this is the solution. General solution with a constant c. Initially there's no salt in it, so we put 0 in for x, and we make that equal to 0, and we solve for this. We have c equal to negative 100, and so the equation is 100 minus 100 e to the negative 0.06 t. And finally, when x equal to 50, we put 50 in for x, and we solve for t. How to solve for t? Move the 100 on both sides. I mean, subtract 100 on both sides, and then divide by negative 100. So I subtract 100, give us negative 50, divide by negative 100, give us 0.5 equal to that. And take ln on both sides. I will do a few of this later, don't worry. And then finally, t is equal to 115 minutes, where the mass of the salt in the tank will be 50 kilogram. So, of course, the solution is here, so that's why I didn't go over much of this. By the way, this is just a differential equation. We did a lot of this on the previous chapter already. The focus here is how to set up a differential equation, which is the application type problem, which we more focus on the application problem. So, look at this example. A large tank holds 200 gallons of some solution. Suppose a flow of 2 pounds per gallon. There's something wrong here. Okay, 2 pounds per gallon solution. No, there's nothing wrong. Enter the tank at 3 gallons per minute. The mixture is pumped out at 3 gallons per minute. If 50 pounds of salt were dissolved initially, so that is the initial condition, x of 50 equal to x of 0 equal to 50. How much salt in the tank after 5 hours? Only set up the problem, do not solve it. Alright, so the first thing is, as always, set it up. Let x of t be the mass of the solute or the substance. at time t. So usually we start with that. Next, the in rate, the rate that coming in. We equal to the rate that flow in. So flow rate times concentration. So when it coming in, what is that? So which the flow enter the tank. So this is coming in 3 gallons per minute. That is the flow rate. And at the concentration of 2 pounds per gallon. Cancel out the gallon. We have 6 pounds per minute. Just put a 6. That's 6 pounds per minute. Right, so that is the rate coming in. Now the rate coming out. Also flow rate times the concentration. Right, the rate that is coming in, coming out this time. 3 gallons per minute. That is the rate. And then the concentration that coming out. Now this is the little, we know the concentration, this is well stirred again. So the concentration is going to be x of t, the amount of salt at time t, divided by the volume. So what will be the volume? Originally, so we have to worry about the volume. Originally that 303 gallons per minute coming in and 3 gallons per minute coming out. So it's always 300. Just spell it out. 300 gallons always, because the amount that coming in and equal to amount coming out. So that equal to 300. And of course that will be amount, will be mass, which is pound over 300 gallon. Right. So 3 over 300 is 0.01. The gallon cancel out. We have pound over minute. Right, so we have the rate coming in, the rate coming out. This is easy. After that, the net rate is the rate that coming in minus the rate that coming out. It's not that bad. The net rate is the rate of change, which is derivative of x with respect to t. The rate coming in, 6, minus the rate coming out, 0.01. I forgot something, right? Times x. 0.01 times x. And so we have that times x of t. So this is the differential equation, which is good. Next, initial condition. Oh, this one is easy. It says that 50 pounds of salt will dissolve initially. So we have x of 0 is equal to 50. So this is the initial value problem. Right, so we have the equation, initial condition, that initial value problem. And the question here is how much salt in the tank after 5 hours. So that's easy. So the problem becomes so we have the initial problem. X prime equal to 6 minus 0.01 x. X of 0 initially that's 50 pounds of salt. And the question that we need to find is what will be in the tank after 5 hours. Notice that this is the unit in terms of minute. 5 hours is 300 minutes. So 300 minutes, how much salt do we have? So that is the problem that we get from that work problem. Right. So like I said, we're not focused on solving this equation. We focus on setting up only. And that's all we do here. Right. Let's look at another example. Consider a large tank holding 1,000 liters of water. Suppose the tank has a very large capacity. We get back to that while we have that. Suppose 0.1 kilogram of salt solution enter the tank at 6 liters per minute. So this is the rate that it entered the tank. So the concentration, the rate. The mixture, I assume that it is well stirred also. That, of course, if without that, we cannot do this one. The concentration have to be uniformly throughout the whole tank. The mixture that leaves the tank 5 liters per minute, and determine the concentration of salt as a function of t. Only set up the problem, do not solve the differential equation. Right, so what's different in this problem? First of all, this problem, the rate that coming in, the flow rate is 6 liters per minute, and it leaves only 5 liters per minute, meaning that it's coming in more than it's coming out. So in this case, the volume here is not a constant. So first, note our volume is not constant. But it can easy to determine, right? Initially, then we start with 1,000. Since it coming in 6 liters per minute, coming out 5 liters per minute, the net rate is 1 liter per minute. It's not constant. And it changes by so coming in is 6, coming out is 5. 6 minus 5 equal to 1 liter per minute. Easy to do that, right? So meaning that the volume, the function will be is a function of t and we have v of t equal to 1,000 plus t, because it go 1 liter per minute. So if it go 5 minutes, it will be 5 more liter. And so the slope is equal to 1 in this case, or 1000 plus t. So this is the function of the volume at time t. Right. So that's the first thing, that this problem is different than the others. But we start with the same thing though. Let x of t be the mass of the substance or the salt at time t. Now the rate coming in we have flow rate times concentration. Flow rate 6 liter per minute. Concentration 0.1 kilogram per liter. Cancel out the liter. We have 0.6 kilogram per minute. Simple enough. The rate coming out of flow rate times concentration. Right, the flow rate 5 liter per minute coming in. The concentration is the mass at the time t, which is x of t, divided by the volume at time t, which is 1000 plus t. And then the unit will be x of t is kilogram, the mass, and 1000 plus t is the volume, which unit of L, liter. Right. So once again, liter and liter cancel out. So we have 5 x of t over 1000 plus t and we have kilogram per minute. So that is the rate coming out, and the net rate coming in minus rate coming out. Yeah, so for this equation, a different story, but like I said, the focus now is only set up the problem. So we do that. Net rate, of course, is the derivative of x with respect to t. The rate in 0.6. The rate out 5x of t over 1000 plus t. That is the equation, right? Initial condition. Consider a large tank holding 1000 liters of water. I assume that it is pure water, otherwise it should say some kind of solution. So initially we have nothing. That is the initial condition, right? Determine the concentration of salt as a function of t. So what is the question? This is the initial condition, right? But the question is, what is the concentration? Right. So, of course, the concentration is this. Of course, there's no 5, it's just x of t divided by 1000 of t. Right, so let's just write the problem. So with all of that, all of this, the problem becomes First, we have the initial condition, the initial value prime, or the differential equation is x prime equal to 0.6 minus 5x over 1000 plus t. That is the equation. The initial condition, initially, there's nothing, there's no salt in the solution in the tank initially, and the concentration will be the amount of salt over the volume. And we asked to find, we will solve for that after we know what x of t divided by 1000 plus t is going to be our answer. So the concentration is going to be that. So that is the problem. Translate from the work problem that we have. So it's not that bad. Setting it up, it's not that bad. By the way, if we need to solve this equation, we move this to the other side. This is linear first order equation, and then integrating factor and all kind of that. But like I said, the focus is not that. The focus is setting up the equation. Right, so that's the first part of the section, the mixing problem. The second part is the population models. So in this case, we study two models. The first one is exponential growth, or could be exponential decay if the rate is negative. Later on, we will talk about exponential decay. Right. The formula is still the same, but it's only different by the rate. Right. So, assuming the ideal condition for growth of a population, meaning that have unlimited resources, no predators, immunity from disease. So because that is ideal condition, usually we don't have any of that. So let P of t be the population at time t. Our assumption is that since it is the ideal condition, it's not affected by any of this. So the growth rate only depends on the population size, meaning the more we have, the more we produce. It only depends on the factor of that, is how much we have at the moment. So the rate, the change of rate of population is only changing by how much we have. P times k is a constant rate. Like if we say the rate is 5%, meaning that if we have 100, then after some period they increase by 5%, increase by 5. So after a period of time, it's 105. If we have a million, we have 5% of that million. It's just so that is in ideal condition. That's how it works. The more we have, the bigger the rate. But it is proportional to the population size. So we have the constant time, the population P. Right. So, and suppose that initially the population is P naught, then we have the initial value from. It's this one. Alright, so of course in this case, this formula we use in a lot of other applications, not just population growth. I could think of, for example, in finance, the interest rate is 2%. That means doesn't matter what we have at the moment, the interest will be 2% of what we have, right? So that is perfect example of this. So continuous compound interest is an example of that. Also, radioactive decay, I will talk about that in a minute. So we have some amount, it will decay over time. The more we have, the more we will lose, because it is decay. As opposed to growth, it is decreasing, but the rate is constant. Only depends on what present at the moment. Right. So, like I said, this formula is for exponential growth or radioactive decay problem in finance, or maybe in all other things too. But those are the first thing that I can come up with. But how do we solve this? Well, move the dt over and move the p down. We have the separable equation. Integrate both sides. So integral of 1 over p dp equal to integral of k dt. Integral of that is ln of p kt plus c. And raise both sides to exponential. E and E and ln cancel out. We have absolute value of p, which is E of c kt. And so remove the absolute values. We have plus or minus. And we did this a few times already. That is still a constant, so it's just a constant times e to kt. Bottom line, with the initial condition of p of 0 equal to p naught, the equation becomes this. Is the model for population growth, exponential growth model. The reason we call that exponential growth because there's exponential function here. P naught is initial population. Right. So the rest of the section, we're not going to derive this formula every single time. We're just going to use that formula. So the rest, this is not really a differential equation. It's more like a Cauchy algebra problem. Right, let's look at some problem. So on January 1st, 2000, the population of Texas was 20.8 million. On January 1st of 2010, it was 25.1. Well, I don't know when we do what is the day for the census, but we do census every 10 years, right? So that's why this year we have the census going. So every 10 years or so, like I said, I don't know exact date, but in here they said it's January 1st, so I'm not sure if it's the date. But we have this information. We estimate the population on Texas in January 1st of 2030. Right. So usually for this kind of problem, we summarize in the table like this. First, of course, we have year. The information will come from 2000, 2010, and then later on, what will the population be in 2030? But of course, this population, this population model, this one might not be accurate because there are a lot of other factors affecting it. Namely, maybe there is a disease or people moving in and out of that environment. Or if there's, for example, in Texas, if there are a lot of jobs, a lot of people coming in, or if we lose jobs, there are a lot of people coming out. So in that case, that certainly affects the population as well. But in this case, we assume the perfect condition. So there will be a model that we follow. Right. Now, it would be easier if we not using those numbers. We say, let's say 2000 is, we start from 2000. So in that case, if we let t in 2000 to be 0, 2010 will be 10 years later, and 2030 will be 30 years later. So for that, we let t be those values, easier to work with. Now the population, we know we follow this model. And in 2000, in t of 0, the population is 20.8. I just write 20.8 rather than a bunch of zeros for millions. 2010 is 25.1. And estimate the population in 2030. So in here we don't know. Right. So we summarize the problem like this. Right. So, by the way, this is a little long, so I will divide the page in two like this. So first, we have the formula. Now let's put this information in. So that is the first thing we do, is putting this information in to the formula. So we say P of 0 is equal to 20.8. So I'm going to put 20.8 in for P. P naught, we don't know, but we later on we know the initial population is 20.8, but we show for that easily. E, K, T is equal to 0. So do this. E to 0 power is 1. So we have 20.8 is equal to P naught. So from the first condition, we get the initial condition is 20.8. Right. Next, we will look at this. Condition, meaning that 10 years later, the population is 25.1. P of 10 is 25.1, meaning that I'm putting 25.1 into P. And initial population now we know is 20.8. E to K, we know that will be 10 years later, right? Right. Now one equation, one variable should be able to solve for T. So to solve for T, first I divide by 20.8 on both sides. Right. And I'm not going to get the decimal approximation, just get a fraction. Because move decimal one place, we have 20 to 51 over 208. Divide that on both sides. E to the 10k. Right. Now we want to solve for k, meaning that we try to get rid of the exponential. What we can do is we can take ln on both sides. So take ln on both sides. E and ln cancel out. We have ln of 251 over 208. And ln and e cancel out. That gives us 10k. Then certainly we can solve for k, right? So k equal to ln of 251 over 208 divided by 10. Right. Just get the decimal approximation for this. Right. Ln of 251 divided by 208 divided by 10. So we have that much, which is about 1.8%, which is reasonable. I'm just write a few decimal places here. Sorry, that would be 10%, but 0.01879. Right. So that is the rate. And then finally we go back to our problem. What is the population in 2030? So now since we have this, so the equation, after this second one, we have the rate of 0.01879. So after that, we have the equation P equal to initial population is 20.8 A, the rate 0.01879 times t. After that, and then 30 years later, so at t equal to 30, I just put 30 in here. On the calculator, I'm going to use the whole numbers here. So 20.8 times exponential, so second ln, and I'm just go up, highlight that number, times 30 years, 30, and we have 36.55 millions. Sound reasonable, right? So that's pretty much a standard population, the problem with the exponential growth. In that model, we summarize the information like this, and then we just substitute each set of data into the problem and find the missing information, right? So that's pretty much pretty standard there, right? So I did mention that the exponential growth, or in this case exponential decay, work for quite others application. Namely, in this case, we have radioactive decay, or we can also works. It also works in finance for the continuously compound interest. The same formula, P equal to P naught, E to KT. But in chemistry, sometimes instead of P, they use Q, which stands for quantity, I guess. Q naught, E to the KT. Right. Same model. Of course, initially there will be Q naught. Right, let's read the problem. Carbon 14 has a half-life of 5730. So the background of this, by the way, the more details, I'm going to put the link in the description. If you want to know more about carbon dating, just look at that, the short video in the link in the description. So here's the background though. Carbon, naturally there will be 12. 12 here meaning there will be 6 neutrons and 6 protons. And in nature, most of them are carbon 12. And there's also carbon 13 and carbon 14. Carbon 14 meaning there will be 6 protons and 8 neutrons. So by abundance, carbon 12 is a lot more abundant at 98.9%. And carbon 13 is about 1.1%. And you say, what's left for carbon 14? And they said, not much. It is about 1 ppt, meaning that 1 part per trillion parts. Meaning that if we have 1 trillion, meaning that if we have, for example, if we have 10 to the 12 atoms of carbon, then 98.9% of them is carbon 12, 1.1% of that is carbon 13, and only one of them is carbon 14. So there's 1 out of that much. Even though with the very small amount like that, it's still we still can track it very accurate. So that's why it's relevant in this case, even though it is extremely small, but we still can count it. That's the idea. Now, okay, so that's how it occurred in nature. The carbon 12 is very stable, meaning that if you have carbon 12 a billion years later or even longer, it's still carbon 12. Carbon 14 is the radioactive material, meaning that after some amount of time, it would change to some other elements. I think it changed to nitrogen, but like I said, it's not a chemistry class. Right, so the idea here is how is that relevant to what we call the carbon dating. So let's look at this chart. So we did say that carbon-12 is very stable, right? Meaning that doesn't matter what we have from the beginning, it will stay throughout the same. So carbon-12 will be constant. It's constant. So look at the chart of carbon-12. And worry about that scale later. It will be constant throughout time. On the other hand, carbon-14 is decay. So the amount of it will reduce over time. Right, this is carbon-12. So let's say initially it will start at the same point. But the reason I write this, the scale is 10 to the 12, mean a trillion more than this, roughly. So if we start with the same amount, and they said half-life is 5730, meaning that after 5,730 years, it will get half to its original amount. In another 5,730 years, it will get half of whatever it is before, and just given half and half and half and half, and so on. So I have this chart. This exponential decay, it is decreasing. Sorry. Okay, so it's like that. So the carbon dating is, since we know the initial ratio of those two, which is about this much. I mean, it is about this much. We just need to calculate what do we have the ratio of carbon-14 present compared to this one, because it is constant. So we just compare to this. So let's say if somehow we look at the case of the carbon, this is carbon-14, sorry. Say the carbon-14 is only 50% of its original state, which is originally it should be like in this ratio of those two, but it only half of it. If it is half of it, then we know it is about 5,730 years old, right? So some certain ratio in time will give us some certain time, so we can date an object. Now, finally, not only that it look reasonable, but why do we use carbon? Because most of living things, including us, make up carbon, right? So when we're still alive, we can eat and we can take in carbon. So we are at the moment at this stage where the carbon-14 and carbon-12 will be kind of constant. But when we die, we could not eat anymore. So the carbon in our body will start to decay. Initially, we have less and less of carbon-14. The carbon-12 will stay the same. I mean, of course, it will stay the same, and carbon-14 will get less and less. And later on, we will look at that, the ratio of the carbon-14 that's supposed to be compared to the original. We can know how old is an object. But usually this kind of problem where we use carbon dating, we work around 1,000 years or so. If it is more than 40,000 years, it is too small to compare, and the calculation is not accurate anymore. So the carbon dating works around 40,000 years or less. If it is more than 40,000 years, like if we have to date a fossil or a rock or something like that, we have to use different element. I think it is potassium 40. But like I said, that's different story. But that is how it works. We just calculate how much carbon 14 we have at the moment compared to what it should be at the initial state. We know how much is the percentage left, then we can date an object. Right, so that's what it is. Next, carbon 14 has a half-life of that, so that's what we have in the chart. Archaeologists uncover some human remains, and we have 76.6 carbon 14 remain in the bone. How old are those remains? Right, so we, but wait, try to make a chart like this. And the problem with exponential decay is, even though we say that is the initial, but it could work with the, even though it could be negative, but still work if we go back in time, it still follow exponential function. Right, so I'm trying to make a table here. I try to write small because we don't have a lot of space left. Yeah, that's what we need. In this case, we're not worried particular year, so we just say t. Let's say right now is years 0. If we want to, we can, let's say right now is 0. Yeah. Even though exponential function is a function of time, population growth, but it could work back in time. It still follow the exponential function, so still work if it's negative in time. So the formula is, instead of P, now we use Q. At 0, the population will be Q naught. 5,730 years later, it is half-life, meaning that it will be half of it. And the question is, how old is that if we have 0.76%, 76.6%, 0.766 of original amount. How old is that? Right, so pretty much like the previous problem. So first, we put this pair of information into our problem. Is equal to Q naught. So in that case, we don't even need to do any math here. So the initial amount is still Q naught. We can put, let's just do that. Q naught equal to, yeah, it looks just silly, right? E to 0 power is 1, so initial is Q naught. So not much we can do there. Initial is Q naught. Next, we put this information in. Q of amount 5,730 years later is 0.5 Q naught. So if we do that, we have put 0.5 Q naught into Q equal to E equal to Q naught times E. K we don't know, but the time we know is 5,730 years. Now, divide by Q naught on both sides. That cancel out. We have 0.5 equal to e to 5,730k. Take ln on both sides. We take ln on both sides. And ln of 0.5 is 0.693, negative 0.693. Right, just like any chemistry major, they know that ln of 0.5 is 0.693, negative 0.693. Or any finance student knows that ln of 2 is 0.693. So yeah, so meaning that 0.5, so it's half-life. In finance, I said, or the most finance students will know that ln of 2 is 0.693, meaning that this is the time that we double an investment. So we do the same thing, but we have, instead of 0.5 initial amount, we have twice the initial amount. In that case, we have ln of 2 instead. And that's why in finance, they should know ln of 2 is 0.693. But here I'm just put ln of 0.5. ln and e cancel out. Oh, forgot the k, sorry. 5,730k. So we just solve for k. And we have ln of 0.5 divided by 5,730. So we do that. So ln of 0.5 divided by 5,730. And we have that much. Negative 1.2 097 times 10 to negative 4. I will just keep that number. Next, the last part of the problem. What would be the time if it is 76.6% left? So we put that information into the equation. So Q of t equal to 0.766 Q naught. And so we solve for t. So put that information in. So we have 0.766 Q naught equal to, on the right hand side we have Q naught e to the kt. I'm just going to put k there rather than put that very long number here. Once again, typical problem, we will divide by Q original amount on both sides. So I have 0.766 equal to e to the kt. And to get rid of the e, we'll take ln on both sides. ln and e cancel out. We have ln of 0.766 equal to e to, by the way, in this case the k is negative, so it makes sense that the amount decrease over time. And when e cancel out, we have kt. So finally, t is equal to ln of 0.766 divided by k, where k is this number. So I just said ln of 0.766 divided by whatever I have previously. And we have 2,000 203.7.67, but like I said, usually this is up, and then that's good enough, so we just say 2203 years. So the object is about that old. But that is the typical population problem. Usually we wrote a table like this, and then we do that. So population at time t and that, and so that's what we have. Right, but of course that is in the perfect condition, in the perfect world. The population, only the rate, the growth rate, or the growth rate only depends on the population at the moment. Or in finance, the growth is constant, depends on how much we have at the moment. So it's the balance, and we just say, let's say 2%, so just 2% times the balance will give us the interest. Or in the radioactive decay, it is constantly declining. Anyway, so if we look at the chart here, we think we still have the chart. We have about 76.6%, right? So it is about this much. So at this snapshot in time, we know if it is about 76.6, it is about 2,203 years. So that's what we have, referring, so we use carbon dating and we have that much. Anyway, just want to put it back on the chart. Right, next is logistic model. This is a little more realistic model of population. So suppose an environment is only capable of sustaining k individual. So that's more like in our world. The Earth can only sustain some certain amount of people. Of course, we don't know how much it can, but let that be k called the carrying capacity of the environment. So if we have a small island, then that island can only hold some certain amount of people. By holding, I mean it has the resource for certain amount of people to live. If there are too many people, there's not enough food, something like that. Right. Suppose that the rate at which population changes depends on the present population and the remaining capacity of the population to growth. Right, so in this case we have R, which is the rate, constant rate. P is the population at time P, right? K is the carrying capacity, which is the maximum, the cap of the environment. Right, so it says it depends on how much room left to grow, like K minus P, meaning that how many people the environment can hold over K. So this gives us a percentage of how much left to grow compared to how much we can have. Right, so with that, and we multiply, factor out the P, we have this R, and so we split this, K over K is 1, K over P over K is that, and then we multiply the R over, that's what we have. Now, after this, if we let R is equal to A, and R over K, all of them are constant, the rate is constant, the carrying capacity is also constant, all of them constant, so we have this equation. Right, also a separable equation, move the dt over, move that over, we have that. Use partial fraction, we split this into two fractions, integrate, and we integrate, we have this. And then multiply both sides by a to get rid of the 1 over a here. And then we use the properties of ln of m minus ln of n is ln of m over n, so we just have that over that. So get rid of 1 over a first, and then since I subtract, it will divide p over a minus bp. Right, of course with ln, if we want to get rid of that, take exponential both sides, and absolute values is plus or minus. And A is a constant, C is constant, everything is constant. So we have this as a constant. That is a constant, so we just say a constant times e to the at. Now multiply this to the other side, and we solve for p. Finally, we have the logistic model given by that. Now divide, if we can divide both sides by e to the at. We end up to this. And finally, assume the initial population is p naught and not equal to a over b. This is the logistic model. The graph of it, if we looked, it would more likely to be, there's a carrying capacity, population original. This is p of t in terms of t. It will look like this. Initially, it grows very fast because there are a lot of room to grow, but when it gets to some certain amount, there's not much room left to grow, so it goes slow and slow, and eventually just flat out. It cannot get more than the carrying capacity. All right. So I just want to go over the formula for the logistic model. We're not going to do any example in this part. So in this section, we only focus on two things, two applications of differential equation. The first one is the mixing problem. The second one is the population models, and we in that population model we only worry about the exponential growth. We might have exponential decay in that too, but still the same formula. The logistic model, I'm just going to introduce the problem, but we will not do any example in that. But that's all the application I want to cover for this section. See you in another video in differential equations. As always, thank you for watching.